Hello and welcome to our next workflow demonstration. So today we are going to talk about this shift knob scan data and how we can get something useful out of this scan. So of course we can see that this is really bad quality scan first of all. A lot of defects, a lot of features that we wouldn't want to see here. But anyway, this is reality and sometimes we have to work with such bad quality data as well. And we have to figure out our approaches in cases if we can't simply rescan all this object to get better data and simply to deal with what we have. So as most of all the geometries and all the parts we can see around us, there are many ways how we can approach this process and how we can build these surfaces or solids. Same goes for this part. Always typically I'm trying simply to rotate the part around and try to catch some geometries to understand how they are flowing, and by doing this I'm just trying to build in my mind some let's say strategy. How will I build all these surfaces and what tools can I use for this purpose? Right now I'm looking at this part and I can see several approaches. So first we can try to fit some primitives, then loft all that together. Probably this might work, but there is never a guarantee that it will work. Same, we can try to create a 3D curves network and then to create a fill surface based on that. Also, we can always use automatic freeform in such cases, but we have to keep in mind that we need to keep it low resolution as possible. So these would be like a couple main approaches that I will try to use here, and I will start with the simplest, or maybe second simplest. And this would be a primitives fitting. And just before I'm diving into fitting primitives exactly, I want to make sure my scan data is aligned to coordinate system, because I will want to create a cross sections and I will want to probably split this part in half to mirror it to the opposite side, because I think it's not like super perfectly symmetrical. So let's go on and do this. Essentially, what's the easiest way how to align this object to coordinate system? In my opinion, we can try to create a symmetry plane and see how it goes. So let's ask software to rebuild this and propose us best symmetry possible for all of this scan data. So we can see it's not like super perfect, but we can't expect anything much more from so bad quality scan data. In general, it holds shape and we can see the middle part is good, here somewhere around corner is good, backside middle part is good. All the rest is slightly away. Of course, it's not like critical, okay, it's like 0.5 millimeters, but first of all, considering this is a shift knob, it may be worn or whatever something. It's not from new car, so based on idea that this part is like 20 years old, it might have its own deflections, warpings, and wear marks all around it. Okay, so I assume this symmetry plane is good enough for me. Let's create this one, and the next step would be to align this candidate coordinate system, and at this point I'm just going to use only this symmetry plane, and I will say this is a right plane, and I will hit apply. Okay, close. So right view, we have this part aligned properly. What I would like to do right now, well, probably I can try to align it one more time by reorienting this lower part to be more or less vertical. Of course, I can always try to do this just in an interactive way by rotating it and saying, okay, this looks good enough for me. Or I can go a different way to create a cross-section sketch. Fit one straight line on this side, another straight line on this side. Select both of them and create a middle line. Okay. Oh, actually, before I'm proceeding, I will just edit the sketch. I will get rid of these unnecessary lines and I will turn this into a regular line. Okay, so now I can go again to align by coordinate system. So at this point, what I want just to select this line and say this is z-axis, and I want to flip it, hit and apply. Okay, we're good to go. So we have aligned the subject to coordinate system as it seems to be best for me. Okay, so once I have done this, I can proceed to recreate the shape with more or less simple steps. Of course, the thing is, when you're looking at these geometries, it's extremely difficult sometimes to realize, to imagine of what shapes it might have been created and in general what approach was used to create these objects. Because if you look at some examples of designing on internet, how guys are modeling something, there are two main approaches. So one, if they would recreate a complete shape from, for example, side view, top view, and front view, trim it, and then blend edges, and probably trim away this top part here. Or another way, which is quite more complicated, where guys are using a lot of 3D curves, then loft all that together with guide curves and everything. It seems simple, but it's simple only when you are designing something. When we have to use the same approach for reverse engineering, that's extremely complicated. And this is something that I'm going to show you later in this video. But now, simple things first. And as I said, I'm going to attempt, first of all, to recreate this object with primitives. So I was looking at this part and I realized that probably initial design was created by having some sort of cone or cylinder from the bottom, and to me it looks like this top part might be just a sphere. So let's try to find out if this will work in such case. So let's say I will try to use this region to fit a sphere here. Let's see deviation analysis. Well, to be honest, it fits quite good. Okay, so I'm going to accept this one and let's try to fit cone somewhere here, for example. Let's see analysis. Well, it kind of fits, not so great. But at this point, I want to try to use this cone just for testing, if this would actually work in such case. I'm just going to make it slightly shorter, edit this and say I don't want this to be a solid, I want just an outer wall. Next step, I need to trim this sphere. So let's create a cross-section sketch like this, and I will draw a line from center of sphere somewhere here, probably. Well, basically where I can spot some more or less flat part that would remind me of blend in between these two surfaces. Let's extend this line, extrude it to create a surface. And now let's just trim these two like this. Okay, so now I have two surface bodies, and now I want to create a loft in between them like this. Okay, and let's see the result. To be honest, it's not that bad. So definitely this approach could be used here. Okay, so now I want to replace this cylinder with some maybe more precise geometry. So let's try and see how we can define just two simple sketches here. Say this one, and here from top view we can see that actually this part is a lot out of symmetry. So let's try to fit here somewhere circle. That would be average of everything. Probably we can try to use this quick fitment tool and move it later to center of coordinate system. It's not like super perfect. It's not too bad as well. So basically I have to try to find some spots that might have enough data to reconstruct the circle more or less precisely here. So in this case, I'm just going to accept this one, and I'm going to create another cross-section sketch. Well, basically around here, I think. Here we can see that the circle is bloating quite a lot to the sides. And let's just try to fit another circle that would represent somewhere the side surface. And now I want to adapt this circle to be closer to shape of my scan data. In order to do that, I'm going to create somewhere here a horizontal line. Then I'm going to use tangent arc to fit the top part of it, so I can see it doesn't bend good enough to complete all the shapes, so I'll just do that in parts. At this moment I want to create vertical axis here, so I will trim this all sketch later and just mirror to the opposite side. Okay, from here I can trim circle, trim tangent arc, add calculated radius to this corner, and I want to do the same here on the bottom side. Somewhere here, for example, trim one side, another side, add fillet. Okay, so now I can delete all this on the opposite side, select everything, and mirror. Okay, good. We have the second sketch completed. So now I'm just going simply to load these two profiles together. If something happening or not, looks good. Looks good, so deviation analysis, it fits fairly well. Front side is not that good, but well, we have to remember that the scan data was far from being that great. Okay, so I will accept this result, and now I want simply to load this sphere and this lofted surface with tangency, continuity. Let's see, deviation analysis. To be honest, it fits quite well in most cases. Of course, we can always try to play around tangency weights. In some cases, this might help to get us closer to the scan data itself, but of course, not always. So I will just leave this to default, and I will accept this. Okay, and now I need to create this cutout here to finalize this surface. And in order to do that, I'm just going to create a simple 2D sketch from side view and say I want to outline mesh like this, and extract primitives. And I will ask software to fit here a curve so I have less manual work to do. Like this. Let's come over to this corner, slightly adjust it. Okay, top side looks good. Now I will just add some extension as a straight lines, tangent to this curve. Now I'm just going to simply extend, not extend, but extrude all this surface and hide my lofted surface and trim all this to have a surface body. Okay, so basically this was fairly easy task to do, but it's always case dependent. The same approach won't work for all parts, and it's just a matter if we can spot some regular geometry, some primitives in design, or all that is just freeform designed by imagined shapes and something. So this approach was easy, and this part was slightly, let's say, on the easy side. Just we had to sit and think about what geometries might be used here initially when this part was designed. But if we're looking at the zebra analysis, it's like completely awesome because these are primitive surfaces, these are stable lofts, and everything is just great. But as I said, not always all of this will work for all cases, and sometimes we will have to apply different techniques that will take much more time, much more consideration, again, much more probably pain and testing and failing, but sometimes we just won't have different choices than to use these techniques. Okay, as the next approach, I think I would like to mention the automatic freeform way. Initially, when we are thinking about automatic freeform and see scan data like this, it's not like a great choice because we know that typically automatic freeform copies all imperfections and everything. But I want to show you one different approach how we can actually use pretty good the automatic freeform way and how we can compensate all of these defects. So I'm going to split this scan data just in the middle to have only one side, or actually I can leave it as it is right now because I have all my coordinate planes aligned, so it should work just fine. So let's go to auto freeform. I want it to be feature aligned, for example. The most fancy algorithm of auto freeform, of course. From here, I can see the scan data might have imperfections in different locations, and I'm not really sure how symmetrical it is. Well, actually I am, because we were creating a symmetry plane and we saw that it's not like really symmetrical. But in this case, I want to use symmetry here along YZ axis, like this. So I will quickly make a preview right now. So we can see this is like super fine mesh, and of course it will result in a lot of imperfections here. So you can see it's like not the actual result that we would like to use in this case. So let's just get rid of this one and do all the same again. Symmetry, YZ, but in this case I'm going to use custom quad count, and let's say 250. So you can see we have way larger quads, and that means that we're skipping a lot of these imperfections, and at the same moment it will be way easier for us to readjust, do some adjustments, fine-tune this sub-D surface later. But I want to try to make it even lower, maybe 150. Probably let's go with 100. So I want it to be like really rough and huge quads here. So I don't know, probably I can try to lower even more. Okay, something like this. So basically from here, if I accept this result, hide the mesh, I can see it's actually nice and smooth. One thing that I would like to get rid of here, probably I would like to have less faces. Of course, we can do this with some different methods, but if we are going deeper in explanation where all those extra edges are coming from, extra faces. So here we can see basically one face, another face is fine. So for example, this edge probably we would like to keep, but here we have another one edge from different corner. So basically, these star points, as they are called, are origins where all these edges starts from. So basically, if I would align this star point on this edge here, I would eliminate one of edges and I would have less surfaces. Same goes to here on the side. Okay, in this case it's more complicated to do here something because if we're using the same layout of patches, anyway we have to move from completely circular to like U-shaped profile, and anyway we will have here some surface edges. But as an example, I think this might work like absolutely well, and plus, while when we are having so big quads, it's like super easy for us to do some manipulations to tweak up our shape and so on. If we need to add more volume somewhere, if we want to make it smoother or something, let's say easy peasy. So we have ultimate flexibility here to actually adapt this shape or influence this shape however we want it to be. So I think this is quite a good starting point. If we are using proper amount of quads, we can get like really smooth result, really quick, without, let's say, almost any work involved here. Of course, if we're talking about like if customer would request you to create a proper CAD model based on all the CAD theories, well, this is not. Otherwise, this is a proper CAD surface. It's smooth, it's nice. You can save this as a step or whatever and use even for manufacturing. So this is like some differences of thinking, what is purely proper CAD model and what works perfectly the same as a CAD model just seems different. And when we are dealing with reverse engineering, pretty often we simply won't be able to, let's say, crack the code how designer designed this part back in days when it was designed. So probably he used somewhere fillets, or probably these were blends, and in such cases it would be like extremely complicated to find exactly where this blend started from one feature to another feature, like I showed you in previous example here. So basically this fits quite well, but if we're talking, can we recreate the shape like super 100% precisely as it was designed ages ago? No, definitely we won't be able, because simply we won't be able to find all these tiny movements, all these different settings. And for example, here when I was showing you about this lofting, it's nearly impossible to find the same, for example, tangency settings that this designer might have used, because just a slight movement changes a lot. We can get really close, but not perfectly the same as it was designed. This is one thing. Another thing is, actually every CAD package uses slightly different settings for everything. So basically you can create absolutely the same features and then create loft between them with same tangency weights, and result will be just a tiny bit different in each CAD package. Well, this is just like some off-topic information that probably you don't need, since we're talking about some options, how we can deal with this case. So this was approach number 2, automatic freeform. Quick, easy, pretty stable, pretty smooth, nice, and easy editable if it's necessary for you. And the next approach here would be more fancy looking, more like CAD modeling related. So basically we would create cross sections, curves, sketches, and later try to loft all of this. Actually, there will be like 2 different approaches, and each of them has different limitations. So now I'm going just to duplicate this mesh here. I will create a plane on YZ axis, not axis but plane. Okay, like this, and I'm going to use this plane to cut my mesh in 2 halves. Okay, I will keep only this one. Good. So from here, what can we actually do? Oh, probably I will trim. Actually, yes, I will trim the bottom side as well, so I don't have all of this closing surfaces here. So let's go again to trim it with plane. Okay, and keep only this one close, like this. So it will be easier to understand and follow up what I'm doing here. So now, first approach would be to come over to Surfacing tab and use 3D sketches to define boundaries of this surface. So let's go. I will use here just like 2 control points, most likely. Let's snap them directly to corners. Okay, this looks good. We can take a look at deviation, and it seems we are pretty close. We have here and here some small bumps, but in general that should work. So let's create another curve along this edge here. Again, I'll just pull it away to snap the edge of this scan data. And now I will try to move control points to make it closer, but from here I can see that most likely I will have to introduce more control points. To have more stability and to be closer to actual scan data. Okay, so let's say this is good enough. Now I need to create another 3D curve somewhere along this edge here. Let's say like this. Let's try to reposition these control points so we're closer to deviation analysis here. Well, not deviation analysis, but closer to scan data itself. Okay, and here's the thing. Since we have this defect here on the scan data, we can see that our curve is following the corner of our scan data. So basically, we would have to move point somewhere here, or there's another option where we can just select this individual point and manipulate with disabled snapping. So at this point, I'm just going to pull it slightly away. So my deviation analysis shows I'm good along this edge here. So it's nice and smooth, basically, as it comes out of the curvature of this blend here, it just goes more or less straight vertically. Okay, oops, not completely okay, but yeah. Let's move to next curve. Now I have to build curve here all around all this long and curved edge. So basically here thing is nearly the same as with freeform surface. The less control points you use, the smoother your surface will be. Not surface, in this case it's just a curve. Okay, so here I can try to snap completely to edge. Here it's slightly more complicated because again it starts to curl somewhere. Probably not the way I would like it to be. But let's see if we can actually manipulate it good enough. To have it around the surface we want it to be. So let's just pull this one slightly. Let's pull this one. Of course, by these manipulations, we're sacrificing the deviation analysis in this case, but we just wanted to follow nice and smooth surface without all this curling over the edges. Okay, so this side looks more or less fine. Let's take a look what's happening here. So plus minus this and this very last one. Let's just pull it something like this. So we have more or less nice and smooth flow of this 3D curve. Okay, so here I can enable my snapping and move around this control point to get closer here on the edge, probably this one. But in general, I'm just going to stop at this point. Okay, probably I want to pull this one slightly away, like this. Okay, so now I have created these 4 3D curves around the boundary of my scan data. And now we can take a look at 2 different approaches from this step down the road. So first one, we have fill surface tool. So let's select all of our curves. Basically, at this point, it just creates some sort of loft/boundary surface based on these curves. And as we can see, we're far away from scan data. So in order to compensate that, we would need to recreate a couple more guide curves in some mystical directions. So that would take us quite a lot of time to figure out exactly what these guide curves should look like and in which positions they should be placed to maintain a nice curvature. But here we have this option, create the surface on scan data. So when we enable this option, basically software creates 5 by 5 fit surface and later trims it with the created boundary curves. Looks pretty okay in general. It's not bad. It's not like super good, but again, we have to remember that initial scan data is far from being good. Okay, it looks, oops, the wrong button. So let's repeat on scan data. Okay. Nice, perfect, smooth surface. If we take a look at analysis, everything is great as well. But here is downside of this tool. Let me just enable last 3D sketch. So here, actually, we can see that these boundary curves are not working anymore in this case because we are using fit surface on this portion of scan data. And this fit surface, it tries to align best as possible to underlying scan data. And these boundary curves are used just to trim this surface. So we can see that on this corner we have a problem, so it's not the same as we would like it to be. And we have this same problem here as well. Same as on this side. Basically, this could be compensated by raising degree of surface, adding more UVs. But again, that would copy actually more of defects of our scan data onto this surface. Of course, they wouldn't be so noticeable as in automatic freeform, but still that would affect the outcoming surface. So in some cases, this tool might work very well, probably if this scan data would be without defects and all these bumps, it would work absolutely great. But here, it's not like a super good result. Of course, still we have options how to deal with this. For example, let's say I have this fill surface. I will create another plane on YZ plane like this. I will just pull it higher, for example, somewhere here. And I will use this plane to trim away some portion of the surface. Okay, after that I'm going to mirror the surface. Let me just hide scan data, and from here actually I can come over and simply lofted then tangent or curvature constraint. But of course this is not the greatest option in this case. In some cases it might work just absolutely fine, but here we can see that it's not that super smooth. Okay, probably we can come over and play with tangency weights to make it smoother, to get rid of that slight crease or something. And the same we can do on this side as well, just to tweak it up a bit. In most cases this might help quite a lot, and probably this result might be useful for you in many cases as well. In this case, well, I don't know, maybe it's not that critical, but for example I can see here the top part, I guess it should be like following edge somewhere here. For example, if we enable just this half of scan data, I think it should be closer following the scan data to avoid all this bump here. Of course, probably we could have created the boundary curve that would end up somewhere here, and we would get much better result. But again, later we have to extend it somehow, and since this scan gearbox shifter is like flowing in all the directions, that might be slightly complicated. Of course, it depends on how skilled you are in CAD modeling, and particularly in surfacing. But, well, in general, this case might work. If we're looking at the deviation analysis, well, on the other side, we're just like 0.3 millimeters away. And this is like not precision part, this is old part and bad scan data. So probably if we create part, for example, printed from this given surface, like 99.99%, no one would ever notice this small difference. But it depends. If you have some mating part on top of it, probably there would be some small, tiny misfitting edge. So these are just things that we have to consider when we are creating something. And now let's move to actual lofting and small discussion about loft and in general maybe about multiple sections and lofting them into one surface. From lofting we expect to have like a really nice result if we try to use all these curves to loft them. But in fact loft is quite complicated tool, and typically it takes length of this curve matches to length of next curve and then tries to form surface in between of them. So basically we can take a look at this simple loft here. Okay, in this case it's not going to work. First of all, I want to probably extrude couple edges here to create some side surfaces and to be able to align to them. Basically, I'm just going to delete this one and this one. Okay, so we have extrusion based on normal here. So let's try to change that, and we need along x-axis like this. Okay. So from here, if we would try to create a loft and let's say it would be tangent here. This would sort of create us some kind of result. Of course, we can influence now this backside by disabling lock of tangency control, so we can manipulate each of them. Oh, in general, you can see the shape, how it's being created, and already now we can see that it starts to fall off here and create here sharper corner. And at this point, if we start to introduce guide curves, hopefully they will match right now to my surfaces, or probably they won't. Yes, they are not. So let's just hide all these surfaces and repeat the same from here. So this one to this one, and I want to use this curve as a guide curve, and this one as well. So we have result, but we can see instantly here starts to form all these weird issues. And this is the reason because all of these surfaces are calculated based on, let's say, divide this curve in, like, for example, 3 or 4 segments, and the same with this one. And later, middle guide curves are being averaged based on all of this geometry, based on basically average from this curve and average from this one. And since all of these guide curves starts to curl quite a lot, like this, and the same goes to this one, somewhere from here it tends to create the guide curve that we don't see, the middle guide curves inside of Loft tool itself. It starts to create it like more or less perpendicularly from this edge here, from this curve, and tries to match it perpendicularly here. And this is the reason why we are getting all of these weird results here. Okay, so probably we can introduce more guide curves and try to split this in several lofts. But also there is no guarantee that we will be able to get the really nice and smooth result easily. So let's say we have another guide curve here. So let's loft from this one to this one, then to this one, and use this as a guide curve and this as a guide curve. Okay, so in this case, it starts to create already a self-intersecting surface, and this is the reason why is it failing. Okay, of course, you have to check always if we have a snap to our guide curves, but in most cases when it starts to fail, it's just because result of this loft creates self-intersection. So yes, as you can see, it's failing. Basically, it should look as a super simple, just draw a couple guide curves and, well, you're ready to go. But no, it's far from that. And if we are taking example from this side, so normally if I took the middle of one side curve and I'm trying to create another guide curve here, I would also have to match it somewhere to middle of it normally. Otherwise it will create us quite unstable surfaces and all the things like that. But still, even for this case, it's a super complicated surface already. And there is like huge possibility that it simply won't work as we expect it to be. Okay, so at this point we start to eliminate slightly these bulges everywhere, but you see, it can take a lot of time by trying and pulling your guide curves here and there to match actually to your scan data. In some cases it might be pretty much simple, in some cases it can be like a super complicated. And as I said at the very beginning of this video, we never know how this part was designed. So basically, according to my first results of fitting primitives and lofting, it looks like it was created as a one complete body and then trimmed. Because currently it would be like super complicated and we would need like really a lot of different guide curves to actually match it. And it would be a good question if result would be worth of that spent time. So it's simply good to know different techniques, how we can approach different geometries or same geometry in different ways. Hopefully you found something useful in this video for your experience, and see you in next workflow demonstration.